Okay, so let me start. So today we are going to look at some algorithmic things like we have already looked at a couple of questions, I think, where even though we did not write down specifically the algorithm, our proof were such that it gives the algorithm. And let me see. Which were them, and then I will mention to you so that you can try to go back and see how to actually write the algorithm. Okay, so before that, many of our algorithms will be based on weighted graphs. So you have a graph, and you have some weights associated with possibly edges, and sometimes other parameters like vertices or many other things can happen. But for the time being, we are looking at edge-weighted graphs. Okay. So we have a graph, and then every edge has some associated real number, and this can basically mean several things. For example, it could represent the distance between 2 points, or like it could be representing some places or cities, or it could represent the cost of building a line between these two, or like a road network or something, or some other cost like transportation cost, whatever. Then it could also mean time, right? So you can say that this is the time that it takes to send something from here to there, or it could mean the capacity, maximum. That just basically can mean bridges or something like that, and then you can say that the maximum amount of flow, right, that can happen in this edge is at most this, right? For example, if you have communication networks, or like you have, let's say, computer connection between several terminals, and then you have say that like each of these lines has its own capacity, right? Or it could be like if you're talking about electrical networks, it could be like things like resistance or many other things. So there are several things one can associate with this. Now take a graph, and then you have like the edges have some associated numbers, and this is basically an edge weight function. Okay. Now one question is like you want to minimize or maximize parameters depending on the context, but for the time being we are looking at minimizing the distance or cost or time, etc., and sometimes you maximize capacity, but we will go into that sometime later. Okay. Now the algorithms that we have looked at before, right? One is that of Eulerian tour, where our proof itself gave an algorithm, right? It says that okay, you can try to start from any vertex, you go along the unvisited edges, and eventually you'll come back to the one of the vertices, and you get a cycle. And once you get a cycle, you can remove these edges, right? And then keep on doing this, and then there is a way to come back and then do all this thing again, so that you get the full Eulerian tour, right? This actually the proof itself was giving the steps how we are actually going to do it, and if you can write it in a nice way, it will become an algorithm. Then we talked about spanning trees, and then I asked you to show that every graph has a spanning tree. And if you think about it, a proof using some of the ideas that we discussed in the properties of the trees, you will be able to come up with a proof which will also give an algorithm. So these two we are not going to discuss in this class. Then other questions are like minimum weight spanning tree, that you want to find a spanning tree but which minimizes the weights. So I will show you a case where this is really important in real life. And then you can talk about shortest path from a vertex, right? Some given a vertex, I want to see what are the shortest paths from starting from this vertex to any other vertex in the graph. And then we might look at, in fact, at least I will do one of them and the other you can do yourself. At is graph searching. There are several ways of graph searching, and here are two very famous ones. One is the breadth first search, BFS, and then depth first search. So these two algorithms also we will have a look. Probably not not in consecutive days, but eventually in this course we will take a look at. Okay, so first we are going to look at a minimum spanning tree algorithm. So there are several algorithms. In fact, we will look at two of them. And the first one is using an approach called greedy approach. So greedy is basically, like being greedy, that, you want to minimize. So what you do is that you look at, all possible edges and then pick one with the minimum weight first, right? So the lowest weight and then you pick it up. And then you add it and then you look at the next lowest weight and see if you can add it to the graph without creating any problem, and then keep on doing this, right? And eventually you say that, okay, once you get a tree, spanning tree, you stop, right? So this is the greediness, like, you pick the one with the smallest weight and then the next smallest and things like that. Now the greedy is basically a heuristic and it does not always work, right, in all kind of problems. But in certain kind of problems, it always works. Like, if you approach the greedy, it will give you the best solution. And this is one of the cases. And while we will not look into the definition, etc., any kind of matroid structure, the greedy algorithm will be effective. So what is matroid structure? We are not going to discuss in this course, unfortunately, but it's another topic for discussion. We will see about it. So now, so we are going to look at this greedy algorithm. What does this algorithm do? It basically picks up edge, right, of the least weight that does not create a cycle. Right? So every time you add an edge, you make sure that it does not create cycle with the existing edges. And you always pick the edges in the increasing order of the way, right? So the lowest one starts first. And once you get n minus 1 edges added, then you stop and say that, okay, I have a spanning tree and this has the least weight. So this algorithm is due to Boruvka and Kruskal. So it was earlier well known in many of the textbooks. You will see only Kruskal's algorithm, but Kruskal and Boruvka discovered it around, I think, 15 years before Kruskal did, and later people have acknowledged it, and now it's called Boruvka-Kruskal algorithm. Okay, so let us see how the algorithm works. So here is the algorithm. So you have an input, which is basically a connected graph with a weight function, let's say W. So G comma W is the input of the graph, right? And input of the algorithm. Then we have output, which is a minimum spanning tree T, right? You are given the set of edges V itself, and then F is the set of edges, right? That forms the subgraph, right? Which is a spanning tree. And its weight, right? The total weight of these edges, that will be weight of it. So this will be the output of the algorithm. So how does the algorithm function? Okay, it initializes F to be an empty set because we start with nothing, and then weight of F is basically 0. And then while you can find an edge, which is not considered so far such that F union E is acyclic, right? Then what you do is that you choose an edge of the smallest weight. Okay, and once you do this, you add this edge to F, and then weight of F becomes weight of F plus the weight of the edge that you added just now, and that's it. So you keep on doing this till there is an edge that once you add it, it will still be acyclic, right? And then you can return the values, right? Vf and the weight of F. So this is the This is the algorithm. This is how it functions. Now, how to implement this is another question. If you are teaching a computer science course, one can discuss what kind of data structures we can use. Can you use a queue or a stack or priority queue? Which one will be the best? And things in that direction. And then you can talk about how much time it takes, like how many number of steps, right? It takes, etc., and how to improve this. So all these kind of questions will be there. But for our purpose, we will not spend much time on that. I mean, of course, you can read on this if you are interested, and it's always a good idea to do that. Okay, so here is an example. So and then we will show. So first of all, whenever you give an algorithm, it is also your duty to actually show that the algorithm is correct. Okay, so we are going to prove the algorithm is correct, that it actually produces a minimum weight spanning tree. Because you can claim anything, right? I do this and then I get a tree, and first of all you have to show that what you get is a tree, right? Then you have to show that what you get is a minimum weight tree and all these things. So these things have to be proved. So we will try to prove that also. Before that, we will look at this example. So you have an electric grid that is to be set up in a country, right? Let's say in India we want to set up a grid linking the cities, let's say Chennai, Bangalore, Thiruvananthapuram, then Mumbai, Hyderabad, and let's say Amravati, Jaipur. And then you have a power station which is situated at, let's say, Kalpaka, right? And then suppose the distances given are as in the table, okay? How should the grid connections be so that we get a minimum total distance of grid lines to be laid, because that minimizes the cost, right? And it minimizes the distance as well as the cost of the grid lines that you want to make. So this is definitely an interesting application, right? And here are the weights given, and these are not the real life weights. I have just taken it from an example because uh, you know I didn't want to spend too much time connecting this, like finding the all possible 28 edge weights, right? I mean, one can do it. I mean, it will be quite interesting also, the actual ones, but it may be slightly, reasonable numbers, I believe. It will work. Okay, so here are the numbers that is given, right? So we have between Mumbai and Thiruvananthapuram, the distance is 1457. Thiruvananthapuram and Jaipur is 1892, etc. Right? Thiruvananthapuram Bangalore, which is not really correct, is 1117, and things like that till Chennai to Bangalore 285, etc. Right? So all these numbers are represented here, and you can see that this basically forms a complete graph on 8 vertices, and all the 28 possible edges, edge weights are given here. Okay, so look at this table, and then you want to see how to do this, right? So how do you do this? So you basically lay down the vertices first, and then you see how you are going to execute the algorithm, right? So let us look at the algorithm. Say that you start with the least edge weight, right? So you start with f and all these things be empty, right? And then you start with the minimum weight edge. So what is the lowest weight edge? So to make things easier, I have just numbered some of the edges in the first few edges in the increasing order. So when I mark this blue one, that says that that is the first one, which is the smallest number, right? So 111 is the smallest number among all these numbers. So this edge, right, which basically connects Kalpakam and Thiruvananthapuram, and this one I will choose first. Right? So I will choose this, and because this is the first edge, it is not going to create any cycle. So I just add it, right? So I add it to Kalpakam and Thiruvananthapuram. Okay. So add this edge. So this is the 8111. I mean 8111, right? Okay. So then what do I do? Then I go pick up the of course, I can add. I mean, the algorithm actually adds to the weight by saying that weight of t is now is equal to weight of f is equal to 111, right? 0 plus 111. And then you look for the next edge, right? So what is the next edge? The second weight is 267, which is between H and A, which is Hyderabad and Amaravati. Right? So Hyderabad and Amaravati, okay, H and A, right? So I add this, and this is 267, right? Well, go for the third one. Third one is Chennai, Bangalore, 385, 285, right? C and B. So at this, then the fourth one, right? Fourth one is, where is 4? I cannot find it. Okay, I think 459, which is between Chennai and Hyderabad. C and H. And of course, I have to verify that it does not create any cycle. So in this case, it was connecting two different components, so it doesn't create a cycle. And to implement this, how to make sure that you don't connect edges of the same component, you can also associate with each vertex a color, right? Whenever I give an edge, I will make sure that both of them get the same color. And then here also these two will get the same color. But then when I add this edge to it, I will make sure that they are of the different colors, right? Otherwise, I will not add it. Once I add it, I will make all of them to be one of these given colors. So each component vertices will have the same color. Then you know that it is going to not create a cycle. This is a simple way to do this. Okay, then I pick edge 5, which is Mumbai, Bangalore, and see if it is okay to add. Mumbai, yes, Mumbai is a different component, so Mumbai to Bangalore I add, and its weight is 473. Right? And this one is 681, I believe, 681, which is connecting A and C, Chennai and yeah. So now this one I cannot add because the weight is okay. Maybe I should use a different one. So this will create a cycle. So therefore, between C and A, I cannot add the edge. So I will discard that edge, right, and then go to the next one. What is the next one? So this is discarded. Not this one, right? The sixth one. So the sixth one. Yeah, this one is discarded. Then I go to 7, which is 727, which is H and B. So H and B again I cannot add because it's also going to create a cycle. So I discard that also. So 7 is discarded. Then comes 8. 8 is 750, which is M and C. M and C. Again, I cannot add that. Right? Okay, so 8 is also gone. And I pick 9, which is 800 between H and K. H and K. Okay. Yeah. So this I can add because they are different components. We'll add between H and K. This H, right? Then what do you have? You have 10, right? 10 is which is J and C, I believe. J and C. Yeah, so J and C I can add because it is two different components. So I add this 837. And then you already got a connected graph, right? So we can now stop, right? And then, of course, There is also a way, you can just add a condition to say that if you reach n minus 1 edges, then you stop. So I have already added 1, 2, 3, 4, 5, 6, 7 edges, which is making the graph connect. So I can now stop and exit. Say that okay, the total weight of this thing is the sum of all these numbers. So what is the W now? So W is basically weight of F is going to be equal to the sum of all these numbers. So this is I think this is the total weight of F is 323. And one need to now show that this is the minimum, but of course that is only for the algorithm proof. Here we have just finished and we claim that this is the minimum weight tree. Okay, just 1 second. Okay, so that is it. So this is how the algorithm works, right? Uh, so we have found the minimum span tree for this graph, right? And in this one is the minimum distance of lines to be laid. This many whatever kilometers. Okay, so now let's try to see how we are going to prove this is the best possible, right? So let us see what does the algorithm actually say, right? How does the algorithm function? So the algorithm starts, by saying that okay, when we pick an edge, right, it does not create a cycle, right? That is the while condition. The condition for the while loop to run is says that when I add the edge e, right, which is to the f, then it is not going to create a cycle. So the first claim now we can make is that whatever subgraph it is going to output, it is going to be acyclic, right? So because every time I add an edge, I make sure that I don't create a cycle. Right? So this is something one can easily prove, right? Now then, the second part is to show that the graph that we get is connected, right? So we prove that, well, we started with a connected graph, right? That is the input, right? Input condition is that we start with a connected graph with a weight function. Now, since the graph is connected, every time you look at some components of, so let us say that there are several components for the F, subgraph F. There is some edge which is going to connect between these two, right? These two components. I mean, like not necessarily these two components. Let's say that if you take one component and look at the remaining parts, because the graph is connected, at least one edge must go from this component to any of the other components. So if in the final output we have more than one component, then just let us look at the case, when this edge, going from one of these components to outside was considered, right? So it was considered at some point in the algorithm, right? And when this edge was considered, we did not add it only because it was going to create a cycle, right? Otherwise, we are picking an edge, and then for the first time, that is the minimum weight edge available at that time, right? And then if you don't add it, that is only because it is going to create a cycle, which means that there is already a path connecting these endpoints, and that will only happen they are in the same component. Okay? So therefore, now one can say that okay, the algorithm also outputs a connected subgraph. So I get an acyclically connected subgraph, therefore it outputs a tree. So this is the first part. Now we have to show that why this tree is of the minimum weight. So to show this is of the minimum weight, we will do the following. Okay, so what we will do is that we will assume that there is another tree which is of let's say smaller weight, or right. So you consider a tree with a least weight, and then what you do is you pick up that tree of minimum weight, right? So I give you a tree and I claim that this is the minimum weight of the algorithm, right? The output, which is the minimum weight. Then you say that okay, there is another one with smaller weight. So what I do is that I pick up your tree, right? And then of course, if the two trees have the same set of edges, it's both the same tree, right? But otherwise, there will be some edges which does not belong to the tree I am considering, but that is part of your tree, right? Now I look at all the edges in your tree and then pick one with the smallest weight. Okay. And then I add it to the tree that I have, right? And of course, it creates a cycle. And it creates a cycle, and once it creates a cycle, and it is a unique cycle, right? It creates a unique cycle. That is something we proved earlier, right? Now, so the edge, that from your tree that I have ordered just now, right? That edge, creates a cycle. But now we look at the weight of that edge, right? Now I claim that there is some edge in the tree that I have, right? Where the weight of the edge is less than the weight of the edge that you, because one of the edges, if I break, of course, it will still become two components. But when I added this edge, if the edge weight was smaller than the edge weight of the other edges, then I would have considered this edge first, right? And when I added this edge before one of the other edges in the cycle, then obviously that would not have created a cycle, right? So therefore, I considered the other edges first because they were of smaller weight, and therefore I have at least one edge which is a smaller weight, which was considered before this. And now what I do is that I add this edge, right? And then remove that edge. I will get a tree where the weight of the tree has changed now, right? And then I can keep on doing this, and the number of edges in which the trees differ, right, has become different, and I keep on doing this till I get the tree that we considered before. I mean, one of the trees. So I can basically go from one of the trees to the other tree just by going through several spanning trees in between, and each time the weight keeps on going in the same direction, and therefore you will get there is an inequality between these two, and then one can show that is always maintained in each step, and therefore the weight of the tree that I started with is smaller than the weight of the tree that you have produced. And this is basically the proof that I get a minimum weight spanning tree. Okay, so I will formally write this. I just wanted to tell you this by looking at the algorithm. Okay, now. Okay, so the correctness of the algorithm. So in a connected graph G with edge weights, right? The above algorithm that we considered, right, constructs a minimum weight spanning tree. So the proof is that first, as we mentioned before, the step 2 of the algorithm, right, where the while loop condition ensures that the subgraph produced is acyclic, and if it is not connected, then as G is connected, some edge must exist that connect a component with one of the remaining components, right? And when we consider this particular edge, right, such an edge would be accepted if it was considered by the algorithm for the first time, and if it was not considered by the algorithm, that means that there is then it is already connected. So therefore, the output must be a tree. Now, suppose T star is a minimum weight spanning tree of the graph. Okay? Now T, which is the output of my algorithm, is equal to T star, then we are done, right? I also get a minimum spanning tree, right? Now, if that is not the case, what I do, I choose an edge which is in E of T, but not in E of T star, because they are different. I have some edge like this. Now, what I do, and this edge is definitely considered by the algorithm, right? Because it is already in the tree T. So what I'm going to say, this is the T star that we have, and the actual tree that the algorithm produced. Yeah, actual tree the algorithm produced has some edges which is different from this, and let us say that this edge may be is the edge. Okay. Now this is the edge E, right? So this belongs to T. Okay. Now once I add this edge, of course, it creates some cycle, right? So I have created the cycle now, right? And this cycle, there's some edge, in C minus T, right? So some edge which is not part of T because T is acyclic. So therefore, even if some of these edges are actually belonging to T, there is some edge which is not part of T. So that is some C minus T, right? So some edge which is not part of T. Maybe it is this one or this one. I don't know, whichever one. So one of the edges which was not part of the tree. Okay. Now let us say that edge is E dash. Now E dash will be greater than or equal to weight of V, right? Why is that? Because if E dash was considered, E dash had less weight than E, then before I considered E, I would have considered E dash, right? So the algorithm only looks at the edges in the increasing order of weight. So since I considered E dash, only after I considered E, right? That is the only reason I did not add E dash, because if I considered E dash before E, then of course I would have added E dash, because before adding E there is no cycle in the subgraph, and I would have added E dash, and then when I come to E I would not have added it, right? If it creates a cycle. So therefore, weight of E dash must be greater than or equal to the weight of E, and it could be equal. It will be at least as much as. So that, which means that the the tree that I can look at, for example, right, T star, let's say minus or T star plus E, which creates a cycle, minus E dash, right, which is an edge which is not part of T, right, C minus T. This is a tree now, right, and this tree, right, because it has created one cycle and I removed one edge of the cycle. So therefore, it's again tree now. And then weight of this graph, right? Weight of this part is basically I have added an edge of weight which is less than or equal to the weight of this. So this is less than or equal to the weight of T star. Okay. But what happened? This T star minus T star plus E minus E dash. This is a tree. And it has one more edge common with T, right? So the number of edges that is common to T now increases by 1, right? Because I have removed one which is not part of it, and I have added one which is part of it. So number of edges which is not common with T decrease by 1. Then I can keep on doing this, right, till I get a tree identical with T, right? So this I can keep on doing, and iterating this, one can show that you will get a sequence of trees, and each of them has weight less than or equal to the previous one, and therefore the weight of and finally it will converge to T itself. So therefore weight of T, right, will be less than or equal to this. So that is the idea. Okay, so more formally, so T star plus E has a unique cycle C, and some edge E dash is in C minus T. And further, we have weight of E dash is greater than or equal to weight of E. Okay, so I have not written down the reason. I explained it before. So you can write down the reason. I have written Y here. So when you write down your notes, make sure that you write it down. Now, therefore, T star plus E minus E dash is a tree with weight less than or equal to weight of T star, and has more edges in common with T, and iterating the you get a sequence which converges to the tree T, and therefore weight of T is less than or equal to weight of T star. Okay, so that is our that's our proof of the correctness of the algorithm. To the next one. Okay. Next, another algorithm which is well known as Prim's algorithm, but it is actually Jarnik who discovered it first. So we will call it Jarnik-Prim algorithm. Okay, again, this finds a minimum spanning tree, but it works slightly differently. It basically you can start from any vertex that you want, and the algorithm outputs a spanning tree where this is the root of where you start with, right? You can get a basically a directed or basically you can get a predecessor function which tells you which are the nodes basically visited immediately from here. So you will get a tree with some kind of an orientation where you can basically go from the root to other vertices. Right? So this kind of and it also outputs a minimum, and every time you basically maintain the connectedness. So you keep on keeping the connectedness of the subgraph that you are looking at, and then you end up with a spanning tree. So you basically grow the tree from a component. Okay. So the input is basically a weighted connected graph again, and output is a minimum spanning tree T, a predecessor function, and the weight of the tree. So that is the works as follows. So for every V, we will say that predecessor is the empty set, initialization, and the cost of the vertex is infinity. Actually, this I am not probably. I mean, this is another thing we can. Maybe we don't need it in our algorithm here. Yeah, so this cost function is probably not necessary. This is some addition that you can do. I have just simplified algorithm a little bit. The cost function can be used to also help me visit at this, and and then also the some additional information can be gained. Anyway, let us simplify the algorithm. So for every vertex, you set predecessor is empty set, weight of t is 0, and t is empty. And then you start with a vertex that you want to start with, right? You pick some vertex, arbitrary vertex, and call it as the root. So this is from the vertex that you are going to grow the tree. And then you have the you set as the set R, skeleton R, where the root is the starting vertex. So what we are going to do is that we are growing S, right? Adding vertices to S till we put all the vertices. So while S is not equal to V, the algorithm functions, right? So choose a least cost edge that is part of a cut between S and S dash. So basically, you are saying that. Yeah, so basically what we are saying is that now you are growing some tree, and then once you have grown some tree, right, you look at the remaining vertices, and then any set with its complement, right, creates a cut. Right? So any set and its complement, all the edges across this. Because the graph is connected, this cut is a non-empty cut. So you look at the edges across this cut, and then pick the smallest weight edge among these cut edges. And that edge I add, right, and to the tree, right, T is equal to T union E, and the weight of T is the sum of the weights of the tree plus the weight of this edge. Then the predecessor of the vertex that we have just picked up. So once I pick up, let's say this edge, let's say this is X and this is Y, right? And once I add Y to S, I'm going to say that the predecessor of Y is X. So basically, this way, right? So I can come to Y starting from the root. I can come to Y once I reach X. This is what the predecessor function. So predecessor of this is basically intersection S, and S is now together with the vertex that we have just discovered, right? A intersection S. Then once this runs, and then you have all the vertices in the set, then you return the tree T with the predecessor function and the weight of the tree. So this will give you not only the tree, it will also tell you how to go from root to the vertices. I will leave it as an exercise to you to prove the correctness. So again, look at the algorithm, write down why every time it creates a tree and it's of a minimum weight tree. And here's the same example which okay. So here I have made it slightly easy for me. Basically, I have just worked it out, starting from a vertex k as the root. Okay, so Kalpakam is the power station. So let me start with Kalpakam itself and then see where all the things. So what I do, I pick up Kalpakam k first, right? I mean, in fact, I pick up k first and then look at the edges which are going from k to the remaining vertices, right? So here are the vertices, right? K to these things and then these two, right? CB. So out of all these numbers, 111 is the minimum one. So I pick up this cut, right? So K to this one. So this will be the first edge that I am going to consider. Right? And once I have this subgraph, now look at this set and the complement as a cut. So for each of these, we have to look at now, right? For K as well as T, right? So K and T, look at the from K to T and T to other things also, and K to other things also, right? And which is the smallest one? Next one. So the next smallest one is from out of K and out of T. There is 800 is the smallest one, I believe, and from everything else is here on, right? Yeah. So therefore, 800 will be added, right? So this is the next one to be added. So now I will look at this as the component, right? So I grow the component to this one. Maybe it looks a little ugly now, but you get the idea, right? You have the component, and once I have this component, again I look at the remaining part we should have. And then look at the thing, and then you will see that S to A is the minimum one out of this. So I will add this one. Okay. Then I make a new thing, and then you look at the next card, and I find that S to C, this one is the next one. So I have this, and then from C to B is the next one, and then B to M is the next one, and then C to J is the next one. So this way, of course, I have to go through this, and you have to basically go through all these things every time to find out the minimum one. And it's a painful process. But if you actually use what is called a priority queue as a data structure, then this can be done much more efficiently. And we will not discuss the data structures here. There are several questions about data structures, how to maintain the structure efficiently, like when to, when you add something, when to basically reorder things, right? And you have to maintain the smallest one at the top of the cube, right? So all these things will be questions for the computer science guys. So we will, for the time being, not discuss those things. Okay. So without worrying about that, try to find out this like this. This is again very simple because we start from anything. Just need to look at the cut and find the smallest weight. Cut. Now, will be another question. So I'll leave it to you as an exercise. So again, because the edge weights are distinct, the both algorithms will produce, no matter where you start, will produce the same tree. You can try it with another vertex and see whether it produces the same tree or not. Okay. So you will again see that we have picked exactly the same set of edges, and therefore total will be our number. What was it? 3232, right? Okay, so this is what, and here the predecessor function is there, like for J we directly come from K, and C it basically comes from H and K, etc. Okay, so that is the thing, and then now I will leave you with the proof correctness. Okay, so the correctness theorem is a homework question. The Jarnik-Prim algorithm outputs a minimum weight spanning tree, and you have to prove it. Let me prove and see what all you need to basically prove. You have to prove minimality, you have to prove this thing, but the ideas will be slightly different.